Have you ever wondered about the nature of the universe and our perception of reality? Well, a lot of it has to do with the groundbreaking concept of space-time, introduced by none other than the brilliant mind of Albert Einstein. In the early 20th century, Einstein rocked our perception of the universe with his theory of general relativity. The theory introduced us to the idea of space-time, an intertwined framework that fuses space and time into a single unified entity. Picture it as a four-dimensional continuum, a vast cosmic fabric where the forces of gravity, the dance of motion, and the essence of reality are all intricately woven together. Everything in the universe, from the smallest particle to the largest galaxy, exists within this space-time framework. It's not just an abstract concept, but the very playground of reality where all cosmic events take place. The genius of Einstein's theory lies in how it reimagined the role of gravity. Rather than seeing it as a force acting between objects, Einstein envisioned it as a warping of the space-time fabric caused by massive objects. Imagine placing a heavy ball on a rubber sheet. The sheet curves around the ball, right? That's akin to how planets and stars warp the space-time around them, creating gravitational fields that influence the motion of surrounding objects. But space-time isn't just sitting around being warped by massive objects. It's an active participant in the cosmic drama, evolving and stretching, revealing the dynamic and interconnected nature of the cosmos. One of the most fascinating implications of this theory is time dilation, the idea that time is not a constant. It can slow down or speed up relative to the observer's motion and gravitational field. It's a mind-bending concept that has practical consequences, from the functioning of GPS satellites to the experiences of astronauts. So, space-time is not just a stage where the universe unfolds, but an active participant in the cosmic drama. It's a testament to the marvel of the universe, a universe that's not just a collection of things, but a symphony of interconnected forces and events, all playing out on the grand stage of space-time. Imagine placing a heavy ball on a rubber sheet. What happens? The sheet warps, dipping under the weight of the ball, right? This simple scenario provides a tangible analogy for one of the most profound concepts in physics, the warping of space-time. As per Albert Einstein's theory of general relativity, our universe is like that rubber sheet, a four-dimensional continuum known as space-time. And the massive objects within it, much like our hypothetical heavy ball, cause this fabric to warp and curve. This warping, this distortion, manifests as what we perceive and experience as gravity. Picture a star, like our sun, nestled within the fabric of space-time. Its substantial mass causes a significant dip in this cosmic sheet, creating a well of gravity. Planets, like our Earth, move along the curves created by this dip, much like a marble would roll around the edge of a bowl. The planets are not merely being pulled towards the sun, rather they are following the curved paths in the warped space-time created by the sun's immense mass. This dynamic relationship between matter and space-time is a constant cosmic dance. The more massive an object, the greater its ability to warp space-time, and consequently, the stronger its gravitational field. This is why Earth orbits the sun and not the other way around. The sun, being vastly more massive, has a greater effect on the fabric of space-time, and so, Earth dutifully follows the sun's gravitational choreography. But this interplay isn't just limited to stars and planets. Everything, from the most gargantuan galaxies to the tiniest particles, contributes to the warping of space-time, creating a complex web of gravitational fields that govern the motion of all celestial bodies. It's a perpetual and intricate tango led by the mass and movement of the universe's constituents. So, what we have here is an endless cosmic ballet, with every twirl, every leap, every step choreographed by the warping of space-time. The heavier the object, the greater the warping, and the stronger the gravitational pull. The universe, it seems, is a stage set for a performance that's as beautiful as it is profound. Did you know that time is not a constant? This may sound like a line from a science fiction movie, but it's actually one of the groundbreaking ideas put forth by Albert Einstein in his theory of general relativity. This concept is known as time dilation, and it's as fascinating as it is mind-bending. Let's take a moment to wrap our heads around this. We're used to thinking of time as a steady, unchanging flow. But according to Einstein, time is more like a river, its current varying depending on the observer's motion and gravitational field. Imagine two clocks, one on Earth and one aboard a spaceship traveling at high speed. If you could somehow watch both clocks simultaneously, you'd see that the clock on the spaceship ticks slower than the one on Earth. That's time dilation in action. This phenomenon isn't just theoretical, it's been proven in many experiments. GPS satellites, for example, experience time dilation due to their speed and altitude. Their onboard atomic clocks tick faster than clocks on Earth, and this difference has to be corrected for in order for GPS to work accurately. But where does gravity fit into this picture? Well, gravity, as Einstein taught us, warps space and time. The stronger the gravitational field, the more time is dilated. So, a clock closer to a massive object, like a planet, will run slower than a clock farther away. This is known as gravitational time dilation. Imagine an astronaut on a mission near a black hole, where gravity is extremely strong. For her, time would pass normally. But if she could somehow communicate with Earth, she'd find that years, maybe even decades, have passed by while she experienced only a few hours or days. Time dilation isn't just a quirky fact about our universe, it's a profound insight into the nature of reality. It forces us to abandon our everyday notions of time as a uniform, universal quantity, and embrace a more flexible, relative concept of time. It's just one of the many ways that Einstein's theory of general relativity has revolutionized our understanding of the cosmos. So, an astronaut traveling at high speeds or residing in strong gravitational fields would experience time dilation. Have you ever looked up at the stars and wondered if the universe is expanding? If so, you're not alone. This question has perplexed scientists for centuries and is at the heart of our understanding of the cosmos. Space-time, that four-dimensional fabric of reality, plays a pivotal role in our understanding of this expansion. It is not just a passive stage on which the cosmic drama unfolds, but an active participant, stretching and warping as the universe grows. Now, let's take a step back, about 13.8 billion years back to be precise. Picture an extremely dense and hot state, where all matter, all energy, everything that would eventually become our universe, was compacted into an infinitesimally small point. This is the scenario proposed by the Big Bang Theory. In an event of unimaginable power and scale, this tiny, dense point began to expand. As it did so, it cooled and matter began to form. Stars ignited, galaxies coalesced, and the universe as we know it began to take shape. But the Big Bang wasn't just a one-off event. It set the universe on a path of continuous expansion that persists even today. And this is where space-time comes into play. As the universe expands, so does the fabric of space-time itself. It's not just that galaxies are moving away from each other within space, but that the space itself is expanding. Observations of distant galaxies reveal this fascinating phenomenon. When we look at these galaxies, we see that they are moving away from us. The further a galaxy is, the faster it seems to be receding. This suggests an overall expansion of space-time, a stretching of the very fabric of reality. This understanding of the universe's expansion, rooted in the concept of space-time, is one of the greatest achievements of modern cosmology. It underscores the dynamic and interconnected nature of the cosmos, where space, time, matter, and energy are all part of a grand cosmic ballet. So, the distant galaxies that we see in the night sky are moving away from us, suggesting an overall expansion of space-time. What happens when gravity becomes so intense that nothing, not even light, can escape? This is where we enter the realm of black holes, the fascinating cosmic entities predicted by Einstein's theory of general relativity. Black holes are regions in space where gravity is so incredibly strong that they create deep wells in the fabric of space-time. Imagine throwing a pebble into a pond. The pebble creates a ripple, a disturbance in the water. Now, imagine that pebble is a massive star, collapsing under its own gravity. The ripple it creates is not just in water, but in the fabric of reality itself. This is a black hole, a place where space and time are distorted so profoundly that the laws of physics as we understand them start to unravel. The gravitational pull of a black hole is so powerful that it curves the trajectories of nearby objects, including light itself. This is why they are called black holes, not because they are dark, but because they absorb all light that ventures too close, rendering them virtually invisible. It's like a cosmic vanishing act, where stars, gas, and dust disappear into the abyss, never to be seen again. But black holes are more than just cosmic oddities. They are laboratories of extreme physics, places where we can test our theories of gravity, space, and time. They challenge our understanding of the universe and push the boundaries of our knowledge. It is in the study of black holes that we find some of the most compelling evidence for the warping of space-time. The way they distort the paths of light and matter reveal the dynamic and flexible nature of the universe. They show us that space and time are not fixed, immutable entities, but are instead part of a malleable, interconnected continuum that can be stretched and warped by mass and energy. Thus, black holes are not just fascinating celestial objects, but they also provide us with a unique perspective on the nature of space-time itself.